In this video, we're going to continue to look at carboxylic acids, focusing on acidity. And we're also going to include another group of compounds that are significantly acidic, and that is phenols. So first of all, what are the features of carboxylic acids and phenols that make them acidic? Well, we can consider two different factors. One is inductive effect, and the other is resonance effect. With inductive effect, it's probably most appropriate to think about the starting material, the acid itself, and we know that oxygen is more electronegative than hydrogen, so this is going to be pulling away electron density, leaving the hydrogen with a significant partial plus. So this is weakening the OH bond and leaving the hydrogen with a significant partial plus, which makes it attractive to a base. Remember, a base is an electron donor. It donates electrons to the H+, or a way that we can think of it is that the base is going to grab the H+. In the case of phenol, we have the same situation. Oxygen is pulling away electron density from the hydrogen, leaving the hydrogen with a significant partial plus charge. When it comes to resonance effect, it's more appropriate to think about the conjugate base. And so drawn here is the conjugate base of a generic carboxylic acid, but we can draw another resonance structure. Imagine these electrons move here, and these electrons move here, and that gives us another resonance contributor that looks like this. So the resonance hybrid, what actually exists for this molecule, is something that looks like this, where we have partial negative charge on both oxygens. Now, first of all, what kind of evidence do we have for this? Well, in the carboxylic acid, we have a carbon-oxygen double bond is 120 picometers, and the carbon-oxygen single bond is 134 picometers. But in the carboxylate, both carbon-oxygen bonds are equivalent at 125 picometers. So they do not exist as a double bond and a single bond, but they exist as equivalent 1.5 type of bonds. So the fact that the conjugate base is stabilized by resonance, that makes the base more stable, which therefore makes the acid more likely to act as an acid and give up its proton to form a nice stable conjugate base. And if we look at phenol, phenol has a lot of resonance because we can imagine these electrons move here, pushing these electrons here, which gives us this resonance structure. We can imagine these electrons move here, and these move onto this carbon, giving us this. We can imagine these electrons move here, and these electrons move onto this carbon. And finally, these electrons can move back, pushing these electrons back up onto the O-, giving us this resonance structure. In other words, the resonance hybrid has partial double bond character between the carbon-oxygen and between each of the carbon bonds of the benzene ring. So there's a partial negative on the oxygen, on the ortho positions, and on the para position. So when we consider phenol, the fact that the conjugate base is stabilized by resonance makes it more likely for phenol to act as an acid because it forms such a stable conjugate base. So when we think about carboxylic acids or other compounds that act as acids, we need to think about acid-base reactions. And if we have acetic acid reacting with hydroxide, that can form acetate plus water, right? So from acetic acid, its conjugate base is, we have the ATE ending, acetate. Acetic acid has a pKa of about 5. Water has a pKa of about 16. And so this equilibrium lies to the right. Now, we could also think more specifically about the acid-base reaction and include sodium hydroxide, because hydroxide is going to grab off this proton and we make the carboxylate, but we can think of it as the sodium salt. So this would be sodium acetate. Here we have benzoic acid, and so here we have sodium benzoate. This is called phthalic acid, and one equivalent of potassium hydroxide will pull off one proton, and we have the potassium salt. So this is potassium hydrogen phthalate. Which is commonly referred to as KHP, and this is used as a primary standard that you can use to standardize sodium hydroxide that you're trying to use for a titration, for example. And this last example, we can have this really long chain fatty acid, and if this is treated with sodium hydroxide, then it will form this. And when we have a whole bunch of these together, they are going to line up like this. Can you hear that car alarm in the background? Forming a micelle. And what happens is that, so we've got this part of the molecule that is this, and this is very water soluble. This part is not water soluble. This is very greasy, and it is going to hang out in the interior when this is in water overall. And so this is soap, and if you have other dirt and other greasy particles, that is going to get pulled into the center of the micelle, and then the whole micelle gets washed down the drain as you rinse the soap off your hands, for example. As we think about acid-base reactions, it's important to think about what species are actually present in solution. So if we have some generic acid HA and it reacts with water, and water is the base, grabs off the proton, giving H3O plus and A minus. Now we can write an equilibrium expression for this, and this is the Ka, H3O plus times A minus divided by the concentration of HA. So remember, a general equilibrium expression is products over reactants. We do not include a term for water because water would be the solvent in this case, and so that is essentially constant. Acid dissociation in water, this is what we use to get the Ka, the equilibrium constant for the acid dissociation, and then from the Ka we determine the pKa, and pKa is what we use to compare acid strength in general. Remember, pKa is the negative of the log of the Ka. From general chemistry, you might remember the Henderson-Hasselbalch equation. If you don't remember this, you will definitely remember it when you are taking biochemistry, for example. So the Henderson-Hasselbalch equation says the pH is equal to the pKa plus the log of the concentration of A minus over the concentration of HA. Now this can be rearranged, and it gives the concentration of A minus over HA is equal to 10 raised to the power of the pH minus the pKa. So let's say we are talking about a particular pH. So at a pH of 7, And we're talking about carboxylic acid, so this has a pKa of 5. So at pH 7, 10 raised to the 7 minus 5, that is equal to 100, and that is equal to the concentration of A minus over HA. In other words, at pH 7, the ratio of carboxylate to carboxylic acid is about 100 to 1. In blood, physiological pH is about 7, and so at a pH of 7, any carboxylic acid that exists in your blood actually exists primarily as the carboxylate. So we're not going to use the Henderson-Hasselbalch equation, but I just wanted to remind you of this. This is a very, very useful equation as it helps you to calculate the pH of buffers. It helps you calculate how to make buffers if you are trying to achieve a particular pH to be able to run an enzyme reaction, for example. It also allows you to get information about the amount of HA and A minus that exist in a particular buffered solution. Next, let's think about the acidity of carboxylic acids and phenols with respect to position of equilibrium when reacted with different bases. So let's start with phenol, for example, and if we treat this with hydroxide, hydroxide acts as the base, grabs off the proton, and we get the phenoxide ion and water. So phenol has a pKa of 10, water it is 15.7, and so this is the stronger acid and the equilibrium lies to the right. Let's look at benzoic acid, which is a carboxylic acid, and this has a pKa of approximately 5. So hydroxide will grab off the proton, give the benzoate plus water. So benzoic acid has a pKa of 5 compared to 15.7. This is the stronger acid. Equilibrium lies to the right. What if we used a weaker base such as bicarbonate? Well, phenol plus bicarbonate, this is going to grab off the proton, giving phenoxide and H2CO3. And H2CO3 actually breaks down to form water plus carbon dioxide, and then carbon dioxide is bubbled off as a gas. So you can often test for an acid by looking for the formation of carbon dioxide bubbles. All right, so with phenol, pKa of 10 compared to hydrogen carbonate has a pKa of 6.4. So this is a stronger acid and equilibrium then lies to the left. That means that if you had a phenol and you reacted it with bicarbonate, well, you're not really going to see much carbon dioxide because very little of this stuff will be produced because the equilibrium lies to the left. In contrast, when we have a carboxylic acid and we treat it with bicarbonate, this is going to grab off the proton, giving this. Now we have a pKa of about 5 compared to a pKa of 6.4. So this one is the stronger acid, and so equilibrium lies to the right. Which means in the presence of a carboxylic acid reacting with bicarbonate, you will see a lot of CO2 bubbles being produced. Next, let's think about how structure affects acid strength. So we can compare acetic acid, propanoic acid, and 2-methyl-propanoic acid. And so here we are adding an extra methyl group, here we are adding yet another methyl group. And the pKa's, this is 4.7, 4.9, and 4.8. So if we're adding an alkyl group, it doesn't really have that much of an effect on acid strength. What if we have a halogen, or two halogens, or three halogens on the carbon adjacent to the carboxylic acid? Again, we want to compare this to acetic acid with a pKa of 4.7. With a fluorine, this has a pKa of 2.6. With chlorine, it's 2.9. Bromine, it is also 2.9. Now, with one chlorine compared to two chlorines, this is 1.3. And with three chlorines, this is 0.9. So each of these halogens is an electron withdrawing group, and these have a big impact by inductive effect. And so the fluorine is pulling away electron density from the carbon, which is going to try to pull away electron density overall, which is going to further weaken the oxygen-hydrogen bond, leaving a bigger partial plus on the hydrogen. Another way you can think about it is with the conjugate base, once the hydrogen is gone, and this is O minus, fluorine is going to help to pull away electron density in general to help spread out that negative charge. That's going to stabilize the conjugate base, which makes the acid more acidic. Fluorine is more electronegative than chlorine or bromine, which is why it has a bigger impact. Now, if we're comparing chlorine to two chlorines or three chlorines, well, the more chlorines, the more electron withdrawing is going to be happening, and so the lower the pKa. One other thing to consider, so let's look at another set. If we have, this is butanoic acid. This has a pKa of 4.8. If we have a chlorine here compared to here, compared to here. So butanoic acid itself is 4.8. 2-chlorobutanoic acid has a pKa of 2.86. Right, so very similar to what we see here, having chlorine on the carbon adjacent to the carboxylic acid, it has a big impact. If the chlorine is further removed, this one has a pKa of 4.05, and this one has a pKa of 4.52. So what we're talking about here is electronegativity or inductive effect. So chlorine is pulling away electron density by inductive effect, which means it's pulling away electron density through bonds, and that is going to fall off quickly with distance. So having the chlorine here has a big impact, 2.86 versus 4.8. Having the chlorine further removed, it has a smaller impact, 4.05 compared to 4.8. Right? As our electronegative group is further and further removed from the reaction site, it's going to have a smaller impact on the acidity. So it's important to keep in mind that inductive effect falls off quickly with distance. Let's continue to think about structure and acid strength. And in this case, we're looking at benzoic acids and phenols, and let's think about how substitution affects acid strength. So benzoic acid has a pKa of, okay, it's actually 4.2, and phenol is 10. If we look at nitro-substituted benzoic acid, we can have the nitro group ortho, or meta, or para, and this gives us a pKa of 2.2, 3.5, and about 3.5. The nitro group will be pulling away electron density, and so making this hydrogen more acidic and also stabilizing the conjugate base. When the nitro group is in the ortho position, it is closest to the reaction site, and so this has the biggest impact on the pKa. When the nitro group is in the meta position or the para position, now this is further away from the reaction site, and so it has less of an impact. When we think about phenol, nitro substituted phenol, again ortho, meta, and para. Ortho has a pKa of 7.2, meta is 8.4, and para is 7.2. So what's going on here? Once again, the nitro group has an impact in the ortho position, less of an impact in the meta position because the nitro group is further away. But when it's in the para position, it has the same big impact as what we saw in the ortho position. Well, keep in mind, now we're looking not just at inductive effect, but also at resonance effect. How do we explain that? When we look at the conjugate base, the phenoxide ion, well, we can draw a resonance structure that puts these electrons right on the carbon that is connected to the nitro group. And so that gives us a negative charge here right next to the electron withdrawing nitro group. So that's not possible with a meta position. So with a meta position, we're just talking mostly about inductive effect, and in general, the nitro group has an effect on the electron density in the ring. But the ortho position and the para position, those are directly connected by resonance with the reaction site. Right? Notice that doesn't happen here because there's resonance within here and there's resonance within here, but there's no resonance between them. Here, we do have resonance between the reaction site and the ring, and therefore direct interaction with the substituent. So that's why we see a difference. Here, the impact is just by inductive effect, and so it falls off with distance. And in the case of phenol, the impact is inductive effect and resonance effect. And so it falls off with distance when it comes to the meta position, but resonance is a factor when it comes to the para position. So this takes care of kind of a reminder about acidity of carboxylic acids and phenols, and it's important to think about acid-base reactions, and it's important to think about how structure affects acidity.